This question says a line has equation y is equal to 3x plus k, and a curve has equation y is equal to x squared plus kx plus 6, where k is a constant. Find the set of values of k for which the line and curve have two distinct points of intersection. Well, now, if these guys, when this line and this curve intersect, we know for a fact that at those points of intersection, they'll have the same x coordinates and the same y coordinates. So what that means is that if we equate y, we can solve for x. So for example, when we can say over here that 3x plus k, y is equal to 3x plus k. So 3x plus k is equal to x squared plus kx plus 6. Now what we have over here is a quadratic equation. And because they've said that we have two distinct points of intersection, that means we should get two distinct values of x at two distinct values of x when we solve this quadratic equation. So we should have two distinct solutions, which means the value of the discriminant should be greater than 0. So what does that mean? Well, first let's just rearrange this equation. So we have x squared plus kx plus 6. All right, now let's subtract 3x on both sides, and let's subtract k on both sides. So we have minus 3x minus k is equal to 0. So we have x squared plus kx minus 3x plus 6 minus k is equal to 0. And now we have our quadratic expression. Now we have a quadratic expression over here. And we know that what we have over here is, for any equation in the form ax squared plus bx plus c is equal to 0, for this to have two distinct solutions for x, the value of the discriminant b squared minus 4ac must be greater than 0. When this is the case, we have two distinct solutions. So if we rearrange our equation and we try to solve for b squared minus 4ac, well, let's just see what the values are, right? So what we have over here is, we have a is equal to 1, b, which is the coefficient of x, is plus k minus 3. So we have k minus 3. And c is equal to 6 minus k. That's the constant term. So now let's solve for the discriminant. So b squared minus 4ac implies that we have k minus 3, the whole thing squared, minus 4 times a, which is equal to 1, times c, which is 6 minus k. And this has to be greater than 0. So let's solve for this. Well, we have k squared minus 2 times 3 times k, which is 6k, plus minus 3 squared, so plus 9. And then we have minus 4 times 1 times 6, so that's minus 24. And then we have minus 4 times 1 times minus k. So we have plus 4k over here. And that's greater than 0. Now, if we group the term together, we have k squared minus 6k plus 4k, so that's minus 2k, plus 9 minus 24, so that's minus 15. That's greater than 0. Now let's try to factorize this. Now what we have over here is negative 15. So that means we have to take the difference of two factors of 15 that give a difference of minus 2. Now which two factors of 15 give you a difference of minus 2? Well, if you take the factors 5 and 3, 5 times 3 is 15. And we know that minus 5 plus 3 is equal to minus 2. So we can say that k squared minus 5k plus 3k minus 15 is greater than 0. So that means k times k minus 5 plus 3 times k minus 5 is greater than 0. So we get k plus 3 times k minus 5 is greater than 0. Now, which values of k satisfy this inequality over here? Well, if we plug in k is less than minus 3, we get this as a negative value and this as a negative value. Negative times negative is positive. So we know for a fact that k must be either less than negative 3, or k is greater than 5. If we plug in any value of k greater than 5 over here, we get a value that's greater than 0. So what we have is a set of values of k where k is less than minus 3 or k is greater than 5. For this particular set of values, the discriminant of this quadratic equation is greater than 0, which means that we're going to get two distinct values of x and therefore two distinct values of y, and hence we have two distinct points of intersection. So for this set of values of k, we have two distinct points of intersection, and therefore this is your answer.